Hey everybody, welcome back. This is Math 35, which is college algebra. We're here at College of the Sequoias in Central California, and we're talking college algebra. Today we're working on inequalities. These are equations that have symbols besides the equal sign. All right, and in our book, it's chapter 1, section 7. It might be different in your book if you're at a different campus, but mathematics hasn't really changed much in a long time. So let's just dive right into it. 1.7 inequalities. And so as I was saying, these are equations that involve something that involve inequalities. And inequality means not equal. So the symbols that we have that relate to that, we have the less than symbol, the greater than symbol, and we could look at less than or equal to. And we also have the greater than or equal to. Okay. And so let's talk about some properties of inequalities. So our first option, if the value of A is less than the value of B, and I add C to both sides, we've got A plus C and B plus C. If A was less than B and we add C to both sides, they still remain in that same relationship. A plus C is now less than B plus C. Then A plus C is less than B plus C. And then that was our addition option. Let's look at our multiplication ones. If A is less than B and C is greater than 0, then A times C is less than B times C. And for each of these, let's start off with A equals 1, B equals 2, and here I'm going to say C equals plus or minus 3. So if I have on A, 1 is less than 2, that's a true statement. And I add 3 to both sides, 1 plus 3 is less than 2 plus 3. That's true. 4 is less than 5. And we look at that down here, the same principle down here. 1 is less than 3, or 1 is less than 2, which means 1 times 3 is less than 2 times 3. That holds to be true. And then the reason why I said C equals plus or minus 3, let's look at when C is negative. If A is less than B and C is less than 0, what happens if I do 1 times negative 3 and 2 times negative 3? This becomes negative 3 and negative 6. Which value is larger, greater? The negative 3 is. So even though I started with 1 is less than 2, I end with the inequality changing directions. then A times C is now greater than B times C. And what this leads to, the easiest way to remember this is when we multiply or divide by a negative value, we need to flip the inequality. Okay? That's the rule we need to do. All right, let's start looking at these equations, inequalities. And we'll start off with simpling, just one variable with one exponent of 1. So a linear inequality in one variable linear inequality in one variable. We can have ax plus b is greater than 0, or we could use less than or equal to, or greater than or equal to. Okay? The way we solve equalities is the way we solve inequalities. Other than the symbol, the inequality symbol. And our single caveat, our single difference, caveat is if we use multiplication or division of a negative, we will flip the inequality. Of a negative, if we use multiplication or division of a negative value, we flip the inequality. Let you write that down. Pause this if you need to. This is where we're going to start doing some examples. Well, we're going to do one example, then we're going to jump to add some more to it before we do the rest. Let's just make sure we do the example with the negative one. That's the easiest one to remember. Let's do negative 2x plus 3 is greater than 4. We subtract 3 from both sides. We bring down the inequality symbol. We've got negative 2x is greater than 1. And if I divide by negative 2, don't forget the negative sign, that causes this symbol to flip directions. x is less than -1/2. And if it's not a negative, the sign stays the same. But solving the inequalities is the same as solving the equalities, other than that single difference. Okay? We do write the solutions differently. So how do we write the solutions? We can leave it with the inequality symbol in there. We can graph it on a number line. And shade the values that work. If we do this and we graph on a number line, for the symbols less than or greater than, we use a hollow point basically an O on the value in the inequality. And if we have less than or equal to or greater than or equal to, we use a solid point. On the number line for the value in the inequality. And the third option we use is called interval notation. I'm going to show all of these in a second for every category that we have. Interval notation. In interval notation, we use two sets of grouping symbols. Parentheses are for hollow points or infinities. And the infinities, hollow points in the infinities, like infinity and beyond. And we will use brackets for solid points. And so these are the parentheses are for less than, greater than, positive infinity, and negative infinity. And solid points are for less than or equal to, greater than or equal to. Let's just go over some examples. Pause this if you need it up longer. So on the number line, start at the left and move right. When you hit the shaded region, start the interval. And when you leave it, close the interval. Close or end. Go with end. End the interval. All right, so let's take a look at it. Our first example, let's start with x is, well, example 1. X is greater than 7. And example 2 is going to be x is greater than or equal to 7. Let's look at the two differences. On both of them, we write a number line. I'm going to put 0 in as a reference. 1, 2, 3, 4, 5, 6, 7. 7's later on. If you're on your own and you're being lazy, you could just put the 0 and the 7. Putting the 0 in helps give a matter of perspective. Which way is the numbers going? As you go to the right on the number line, the values increase. And as you go to the left on the number line, the values decrease. We go all the way to the right, this is positive infinity. And if we go all the way to the left, it's negative infinity. Okay? So x is greater than 7. I start at the 7. I put a circle on it. The symbol tells me whether or not to shade it in. The greater than symbol says no shading on the 7. The greater than symbol says shade the 7. So I'm going to fill that 7 in on this one and I'm make it a solid point. But on the x is greater than 7, without the inequality, we're going to use a hollow point. I'm going to put a little bar on my 7 like that, because that way it's a little more distinguishable from the greater than sign. Looking at it, I realized that could be misconstrued. That's why people put that bar on the 7. I've seen that bar on the 7s before. Never really stopped and thought about why they do it. All right, so now we need to shade values that work. If you're unsure what to do, it's always handy to plug in 0. And then if it's true, shade that region. If not, don't shade the other region. What I mean by that, let's plug in let's do x equals 0. Is 0 greater than 7? No. Don't shade towards 0. So what I'm going to do, you have a couple options. MATLAB does this. They just shade the number line like that. What I like to do, so I showed it on that one, on the x is greater than 7. On the x is greater than or equal to 7, what I tend to do is do this. I make a line coming up out of the circle and then do an arrow above the number line pointing in the direction that works. I think that's easier to see on a number line. If you're doing it by hand, you got to do a lot to make sure it's not just a thick line. You need to make sure it's clear that you're shading one direction. If you draw an arrow up and out of it to the right, like I did here, that makes it clearer. Now, for the interval notation, I said start on the left and move right. So I start at negative infinity and I'm not hitting the shading yet. I slide my pencil to the right and I start hitting the value at 7. My interval starts at 7. Starts at 7 on both. On x is greater than 7, I have a hollow point, so I'm going to use parentheses. On x is greater than or equal to 7, I have a closed point or solid point. So I'm going to use a bracket. Then I keep sliding the pencil until I get to where the interval stops. The interval doesn't stop on the number line. It keeps going to infinity. So I will put infinity in. And infinities always get parentheses. And I'm not sure if I covered what infinity means before this in a previous video. Infinity is the largest number possible. Or is the concept of a limitlessly high number. So you could have 15 quadrillion. I don't even know what a quadrillion is. I just made that up right now. 15 quadrillion quadrillions. So a quadrillion quadrillions. And still, that's not the largest number possible because you could always add 1 to it. Infinity is the idea that it's the furthest possible value from 0. And in all reality, you can always keep adding 1, so infinity does not have a value. It has no value or no fixed value because you could always add 1. Because you can always add 1 to a fixed value. So it's just the unendingly large number. And we use a sideways 8 for it. It's often depicted on things as a snake biting its own tail. Time, it's often used as the symbol for time. In fantasy stories and stuff, time without end. This time keeps going on forever. And let's get back to this hollow point and this solid point idea. The hollow point in the parentheses says go all the way up to the value, but don't include the value. The exact value. So on x is greater than 7, I can't use x equals 7.0. But I could do x equals 7.0000000000001. It's just slightly above 7. Okay? On the closed value, closed or solid point, we include the value. For the closed solid point and bracket, the value is included in the solution. Now let's go the other direction. It's not much different. That was my greater than or equal to. Let's look at less than or equal to. Let's change it, use a different number. The 7 looks too much like the inequality. Well, now that I'm using the less than, it won't look like it, but either way. Example 3, example 4. In fact, why don't you guys try what I just said and see if you can figure out what the less than does. Let's use x is less than 2 and x is less than or equal to 2. Try doing the number line and try doing the inequality and see if you can translate what we did with the greater than ones. Let's see if you can get it to work on the less than ones. See if you can figure it out. If you can figure this out on your own, you've got this topic mastered already. The interval notation is a lot harder. All right, so I'm going to put my number line in. 0, 2. I don't, in the long run, you don't need to put the infinity signs at the end. But while you're learning it, it's handy to do so, especially for the interval notation part. In both circumstances, I have 2, so I'm going to put a circle on the 2. For x is less than 2, I'm going to leave it hollow and shade to the left or do the arrow pointing to the left. And for x is less than or equal to 2, I did the same thing, but I fill in the 2. When I'm doing my inequality or my interval notation, I start at the left and I go until I hit the graph or shaded area. The shaded area actually starts at negative infinity. So in both cases, we have negative infinity. Negative infinity always has parentheses because we're not including it. Parentheses mean include, or brackets mean include. Parentheses means don't include that value in the solution. And we keep moving our pen and the pen gets to the 2. Once it gets to 2, we stop shading. So that's our cutoff point. We use comma 2. Two on x is less than 2 as a hollow point. We don't include 2 in the solution because 2 less than 2, no, it's false. It doesn't work, so we don't shade it in. And we use the parentheses here. 2 less than or equal to 2, yes. It's not the less than part, it's the equal part. So we shade it in, we include it, we use the bracket. Okay. That's interval notation. And we can kick it up a notch. Example 5 is when we have two inequalities going on simultaneously. Let's say x is greater than 2 and x is less than or equal to 5. I'm going to leave some room on your when you get to the number line, because I'm going to show there's another way of writing that one. So I've got 0, 1, 2, 3, 4, and 5. Got positive infinity on the right, negative infinity on the left. X is greater than 2. I put a circle on the 2. And I draw a line going to the right. Values greater than 2 are to the right of 2. For x is less than or equal to 5, I put a circle on the 5. I shade it in because it's got the inequality. And then make an arrow going to the right or left. Both conditions have to be met on this part, which means it's only true right here in the middle. Between 2 and 5 is where the arrows overlap. And we still do the circles on the end. So this looks a little bit like music note or headsets or a wagon. Kind of looks like a wagon, right? The other way of writing this without interval notation yet, x is less than 2. If I change the order, I can rewrite this as 2 is less than x. Or x is greater than 2 is the same thing as 2 is less than x. And then I have x is less than or equal to 5. I can smoosh these together. Two is less than x is less than or equal to 5. That is how you will usually see it. When you have two inequalities that cross, we want both regions. We want the overlap of both regions. This goes with the word and. X is greater than 2 and x is less than 5. If it says or, either region works. So wherever it's shaded counts. So wherever any line is shaded. Okay. Before I continue, I'm just going to give a different example. Let's do a different example. Let's use 1 is less than or equal to x, which is less than 6. This tells me x has to be between 1 and 6, and we include the 1 but not the 6. I'm going to put a circle on the 1, a circle on the 6, because they're both in the inequality. The 1 has a less than or equal to portion. I'm going to shade it in, and I want values between them. Okay, if I do interval notation, I'll have you do interval notation on the top after I do it down here. Go back and change it, or write the interval notation on top. Remember, we start at the left, we go to the right, and when we hit it, we start writing the interval. The interval starts at 1, and it's got a solid point. We're including it. I'm going to use the bracket. The interval keeps going, and it stops at 6. So I'll say comma 6, and 6 is not included, so I'm going to use parentheses. That's my interval notation. The reason why they call it interval notation is the solution is on the interval from 1 to 6. Interval is a region. Okay? Why don't you go back and see if you can write this one up here as in interval notation? All right, I'm going to assume you did. We want the shaded region, the red region, so we start at 2. We don't include the 2, so we have a parentheses, and the interval stops at 5. The 5 is shaded in, we include it, so we put a bracket. Okay, a little bit more. Do one more. What was that example? Oh, well, I did 1 is less than or equal to x less than or equal to 6. Let's call that example 6. So example 7. -1 is less than x is less than 0. Put a circle on the 0, a circle on the -1. Neither of them is filled in, and we want the region between them. So in interval notation, this is -1, 0, and both sides get parentheses. And this is the scenario that makes me hate interval notation. When we start graphing, values on the XY plane, This looks like a coordinate. And when we graph XY plane, we usually list points as X comma Y. It's not. This is an interval. So be prepared of seeing something where it you have parentheses on both sides and it's not an interval later on. I think that we start doing in chapter 3. Okay. There is another scenario that pops up quite frequently. Believe it or not, this one shows up a lot. The and problems. This is -1 is less than X and X is less than 0. That's the same kind of idea. I could write it like that. Or I could write it as X is greater than -1 and X is less than 0. When you switch which sides the X is on, like I did here, you just make the mouth chase the larger number. And problems sound, and is in the word sandwich. And so X is sandwiched between two values. As opposed to that, we could have or problems. For example, let's do example number 8. X is less than or equal to -2, or X is greater than 3. Zero in the middle, 2 to the left is -2, 3 to the right is 3. The OR problems are going to give us 2 separate regions. So the X is less than or equal to -2. I put a circle on the -2. I fill it in because it's got the equal portion. And I'm going to draw an arrow to the left towards -infinity. And X is greater than 3 is over here. Put a circle on the 3. We don't fill it in. And that's values greater than 3. It gives 2 regions because X can't be both at the same time. You got positive infinity over here. It's either less than -2 or it's greater than 3. Interval notation. Let's show you how we're going to do it. We start the interval. The interval starts immediately at -infinity. The infinities always get parentheses. The interval keeps going and it stops at -2. So I'm going to say comma -2. It includes -2, so I'm going to put a bracket. I keep going. The interval restarts at 3. So I'll put a 3. It doesn't include the 3, so I'll put a parentheses. And it keeps going until it hits infinity. So it goes without n. We have positive infinity here, parentheses. With 2 or more regions, When we have two or more regions, we use a capital U. It tends to be a wide U, and it means the union of regions. I'm going to put a capital U right here in the middle, and we make it kind of wide, a little bit back. It means we have one region. It could be in one region, or it could be in the next region. So there, I just gave you the regions, or I gave you the inequalities. Now let's just do some with equations. Actually, I'm going to show you something else. Here is a secret tip for identifying where to shade. Secret tip, pro tip on where to shade. And this requires X to be on the left. Or the variable, let's say the variable. It's not always X. To be on the left. X is greater than 1 versus X is less than 2. We put a circle on our values. X is less than, or X is greater than 1. We put a circle on the value. When X is on the left, the inequality symbol is the arrow on the shaded region, is the arrowhead on the shaded region. So the inequality is like that. I'm going to have an arrow that looks like that. And I can't have, there's no way that works over here on the left. So it's got to be coming out and going to the right. Looks like the arrowhead. X is less than 2. It looks like the arrowhead of an arrow pointing to the left. Doesn't work if I have it coming in from the right and pointing to the 2. When it's going out of the 2, it's got to go to the left. Okay? It only works when X is on the left. If it doesn't work, if X is not on the left, it doesn't work. All right? So let's do some examples that, some examples with work in them. Some steps to solve. So let's start off with our first example. I'll go with example A now that we're doing some actual work. 3 minus 4x is greater than or equal to 2x plus 8. You got two ways of solving this. If you like keeping x on the left, so this will be our first way of solving it. I would move all my x's to the left by subtracting 2x. So my inequality is going to come down greater than or equal to negative 4x and negative 2x makes negative 6x on the left, 0x on the right. And since I'm moving all the values to all the x values, the variables to the left, I'll move my constants to the right by subtracting 3. And 8 minus 3 is 5. Now we solve for x. I need to divide by negative 6. When I divide by negative 6, I get x and negative 5, 6. But it was a negative sign, so I need to flip the inequality. I divided by a negative. Got to be less than or equal to negative 5, 6. Now, before I graph it and write the interval notation, let's say you like keeping the coefficient positive. If you like positive coefficients. Remember, coefficients are the number in front of the variable. We'll do the same problem, 2x plus 8. Here, I'm going to add 6x to both sides, or 4x to both sides to get it off of the left side. My inequality comes down, and I've got greater than or equal to there. 6x is on the right, no x on the left, which means I'm going to subtract 8 from both sides. Three minus 8 is negative 5. Finally, I divide by 6. I've got negative 5, 6 is greater than or equal to x. Notice I solved it both ways, and this is kind of like what I was telling you. If you move which side the x is on, you got to change the inequality. These two have to be the same. So when you swap which side the variable is on, you need to change the direction of the inequality. In both scenarios, we've got 0, negative 5, 6 is a little bit to the left of it. If you want to put in the negative 1, you can. Negative 1's right there. On the top one, I can just use it right away. With the x on the left, it's the arrowhead, right? We talked about that. So I put a circle on the negative 5, 6, fill it in, and point an arrow to the left. So the shading's easy to do when you have x on the left. When x is not on the left, when you got it on the right, I recommend test x equals 0. If it's true, shade that. If it is true, shade towards 0. If it's false, shade the other direction. So I'm going to test that. Is negative 5, 6 greater than or equal to 0? No, it's false. So I'm going to shade away from 0. Shade away from 0. Because it's false. Now, you may not like this testing method, but in a little bit, we're not going to have a choice. You're going to have to test values. This test method always works, okay? The testing method always works. This arrowhead method works only when X is on the left. So I'm going to emphasize, I'll put that in words right here. The inequality as an arrowhead only works when X is on the left. Testing values, and then shade if it's true. Don't shade if it's false. Always works. Okay? All right, so that's how those work. Let's see, what did we do last time? Nice. Now, there's pros and tips. Let's go back and look at this page for a second. There are pros and cons to each method. If I force X to stay on the left, I might end up with negative coefficients, and it's easy to forget to flip the symbol. In fact, when you get to the 1.8 video, I made it earlier because it's not very long. I made it before this one, which is longer. This video is longer than 1.8. 1.8 is relatively short. When I was making the video for 1.8, I forgot to flip the inequality, and I saw right away that the graph was not going to work. And so I had to pause and go back and think about it. You'll see when you get to 1.8. It's easy to forget flipping the inequality when you divide by a negative or multiply by a negative. But it's easier to graph and use as an arrowhead. By moving it so the coefficient stays positive, I don't make the mistake of, or I don't have the problem of dividing by a negative number. The sign stays the same all the time. And then I can just rewrite it at the end. I've got negative 5, 6 is less than or equal to X. I can always rewrite that by flipping the sign. Okay? I recommend keeping the coefficient positive. So I recommend keeping the coefficient positive, or solving such that the coefficient is positive. If X is on the right when you get to the end, or when you finish, you can always put it on the left by switching the inequality. Switching or flipping the inequality. If I've got negative 3 is less than X, and I want to put X on the left, negative 3 on the right, I flip the direction of the inequality. Something that might help you is pretend this is a little alligator mouth or vampire mouth. Vampire is chasing X. When x moves to the left, the vampire mouth changes directions to follow it. To follow x. Maybe I should use red for my teeth, because vampires get blood on their teeth, right? Another way you can look at it is Pac-Man. Waka, waka, waka. -3 is less than x. And when I put x on the left, -3 on the right, Pac-Man still wants to chase x. Pac-Man. I know, it's an old video game, but I've seen it in a video game movie just a few years ago, so I know it's not out, completely gone. All right. So let's do a little bit more. We got some more to do in this section. We're not done. Let's give you an example to work on. You try. And we're going to kick it up a notch. One is less than or equal to 6x minus 8, which is less than or equal to 4. Now I can't say either side because I've got more than one region. So normally when we'd solve, if I just had the 6x minus 8 is less than or equal to 4, I would add 8 to both sides, like that. If I had 1 is less than or equal to 6x minus 8, I would still, I'm trying to get x by itself, add 8 to both sides. So I'll put plus 8 over there. When I have two inequalities, look at that. I'm adding 8 to 3 different regions. One plus 8 is 9, and 4 plus 8 is 12. An operation in one zone must be done in all. Three Musketeers, baby. One for all and all for one. Three Musketeers like the candy bar, or not like the candy bar, like the story, not the candy bar. I just said that completely wrong. All right. Again, that principle applies here. If I do it here, I gotta, what I do in one zone, I gotta do in all. So if I want to get x by itself, I need to divide by 6 here, which means that I gotta divide by 6 over here and divide by 6 over here. Divide the 9 by the 6 and 12 by the 6. My inequalities keep coming down. I did not divide by a negative number. If I did, both inequalities would change signs. 9 over 6 simplifies to 3 over 2 is less than or equal to x, and 12 divided by 6 is 2. It might help you to rewrite fractions as decimals. 3/2 is 1.5. So 1.5 is at between 1 and 2. I put a circle on it, a circle on the 2. I fill them in. I fill them both in because the inequality is the same, less than on both of them. And I connect them with a little line. In interval notation, this starts at 1.5 and ends at 2. We include both values. If you try to switch something where you round it, like if we had 5/6, leave it as 5/6. Just make a decimal to see where you're graphing it, okay? We got 2 more types of inequalities we're going to solve. These were linear inequalities. Let's look at quadratic inequalities. Ax squared plus bx plus c. We got greater than 0 or less than or equal to, or less than or equal to, or greater than or equal to. Any of those symbols in there, but it's the one side is quadratic. When we solve quadratic equations, we get 2 values. Equations. We get 2 possible values for x. And they may be the same if they overlap. For inequalities, we call these critical values. Critical values. In a quadratic equation, when we get it down to an answer, these critical values break up a number line into regions. And we must test every region. And it's very important to note, and the reason why I'm saying it now is because oftentimes this is the case. Do not assume that the regions will alternate with shading on and off. Do not. Often they alternate. But repeating solutions and things like that can mix it up. Can mess up the alternating pattern. And I haven't shown you it yet, but you're going to see that they often alternate. So when we test every region, test each region with a value of x in the region, the value in that region. If it makes a true statement, shade the region. If it's a false statement, don't shade the region. Okay? Only way to do this is start doing some examples, and you'll see how it works. So example. X squared minus 2x minus 15 is less than or equal to 0. We're going to solve it just like there's an equal sign in there. Solve just like if it was equal. That means I'm going to factor it. And I get x minus 5 times x plus 3 is less than or equal to 0. And I'm going to pause there. Whoa! Darn near knocked my camera off. This makes a great test inequality. Once you've got it factored, it makes it much easier to test here. Ideally, you test in the top one. In the original inequality. Assuming you don't make errors, you can do the inequality here. So what would I do if this was equal? If this was equal, I would say x minus 5 equals 0 or x plus 3 equals 0. So x equals 5 or x equals negative 3. These are my critical values. I recommend doing the circles and shading them right away. So I've got negative 3 gets a circle, 5 gets a circle. Those are my two critical values. And the inequality had an equal portion to it, so I'm going to shade them in. And then this is not to scale, but I want to test values from each region. So it might help to, put like a little dotted line up showing different regions. Less than negative 3 is one region. This is region 1. I'll call it region A because I'm using number lines. Region B will be between negative 3 and 5. And region C will be greater than 5. I want to test values from each region. 0 makes a great test value because it's easy to do in problems. So 0 is going to be one of my test values. And then I try to pick values that, if I can, that are nowhere near the values I'm looking at. So maybe negative 100 is a long ways to the left of negative 3. Positive 100 is a long ways to the left of or right of 5. And then I'm going to test those values in my equation. Okay? So x minus 5 times x plus 3, is that less than or equal to 0? Minus 5 plus 3. I'm going to do that in each region. Minus 5 plus 3 less than or equal to 0. And then I'm going to plug in the value I've picked as my test value from each region. On region A, I'm going to use negative 100 for x. Let's just work through that real quick. Negative 100 minus 5 is negative 105. Negative 100 plus 3 is negative 97. Is that less than or equal to 0 is a question mark. All that really matters is the region positive or negative. With the test value. It doesn't matter how much it's less than 0 as long as it's less than 0. And so I don't need to multiply 105 times 97. I don't care what the value is. I have a negative sign times a negative sign. What does that make this overall region? It makes this a positive value. Is a positive value less than or equal to 0? No. Now I'll check the 0. Put in 0 and 0. 0 minus 5, plugging in 0 is nice because then you just use whatever's in there. I've got negative 5 and times 3. I can do that. That's easy math. Is negative 15 less than or equal to 0? Yes. And finally, I'll do the 100 on region C. 100 minus 5 is 95. 100 plus 3 is 103. Is that less than or equal to 0? I don't know. I've got a positive times a positive. That's going to give me a positive value. Positives are not less than or equal to 0. No. If I apply what I did here, it doesn't matter if it was 5 and 3. This was a negative times a positive. A negative times a positive results in a negative. Negatives are less than or equal to 0. All right, since I made that kind of messy, I'm going to come down here and do a new number line and do the shading down here. So I had negative 3, I had 0, I had 5. In both cases, the circle is filled in and shaded. Negative 3 was no region or false. 0 was a true region or yes, and above 5 was false region. I'm only going to shade the regions that are true. So I'll connect it like this. In interval notation, we've got negative 3, we've got 5 is where they start and end. We include the points, so we use brackets. We started with x squared minus 2x minus 15 is less than or equal to 0. That led to x minus 5, x plus 3 less than or equal to 0. Less than has the and sound in it, less than, and, sandwich, is often the case. It's not always true. I'll do an example at the end showing where it's not true. Okay? Ready for another one? So let's just write down our pro tip there. I didn't do the calculations in each regions. I just checked for positive or negative. I'll apply that principle again on the next one. Let's do it again. Another one. Oh, wait. You need to have longer. Hit pause. Get a little hasty when I got no one in the room. Talking to a blank wall. It's not all that exciting. But you do what you gotta do. Where's my little figures that I like to use? All right. Huh. All right. Example. X squared plus 6x plus 8 is greater than 0. This factors to x plus 4 and x plus 2 is greater than 0. And so my critical values are going to be -4 and -2. If we set each of those parentheses equal to 0 and solve. So I put circles on the 0 or the -2 and the -4. I do not fill them in. This gives me 3 regions. I need to pick a test value for each region. The right region, greater than -2, 0 is in that region. I'm going to use 0 wherever I can. Between -4 and -2, well, -3 is in that region. I'll pick that. I try to use integers where I can. You can't always do that. Like if you're looking at between 0 and 1, you have to pick a fraction. But here I was able to pick an integer, so I did. And just to illustrate my idea of you don't need to worry about the values, let's go with -1 billion over here. So what am I doing? I'm plugging that in. We've got x plus 4, x plus 2, is that greater than or equal to 0, or greater than 0? And I'm plugging the -billion into each. If I have a -billion and I add 4 to each of them, or I add 4 to a -billion, it doesn't matter what it is, that's a negative number. Adding 4 to the -billion doesn't really change it much. Adding 2 to it doesn't change it much. It's still negative. I could write out a value for it. It's got a lot of 9s and a 6 and then a lot of 9s and an 8, but I'm not going to do it because it only matters whether it's negative or positive. X plus 4 using a negative number, even if I could use -5 if I wanted. That makes it easy. But then I think I would calculate it. Using a negative number that's really big makes it really clear. The -billion is way bigger than 4 or 2, so that adding them together is going to end up with a negative number. Negative times a negative is a positive. Positive is greater than 0. This is a yes zone, or true. I use -3, -3 plus 4, -3 plus 2, -3 plus 4, the 4 is bigger, so that's positive. -3 plus 2, the 3 is bigger, so that one's negative. And a positive times a negative is a negative, which is not, negative is less than 0. This doesn't work here, it's false. And finally, I plug in 0. The zeros just go away. I've got 4 times 2 is 8. 8 is greater than 0. That's a yes. That's a true zone. So when I'm done, I'm going to shade in the direction of the true zones. Goes like that. The true zones are right there and right there, but not in between. And this is what I meant by alternating: true, false, true. If you looked at the last one, false, true, false. It alternated whether it was false or true. You can't assume that. So if I'm doing interval notation here, we start at -infinity. We go up to -4 and we stop. We don't include -4, so we'll do a parentheses. -infinity gets a parentheses. Then we start up again at -2. We use parentheses because we don't include it. We go up to positive infinity. Since there's 2 regions, we're going to use the union symbol. So that's what it is in interval notation. Here I had the greater than sign, greater, greater. Sounds like or. Sounds like greater. And an or is 2 regions. Again, this is often true, but not always. So let me give you an example where that doesn't work. Show you a couple things where alternating doesn't work. Let's say I've got x squared minus 4x plus 4 is less than 0. If I factor this, this is x minus 2 times x minus 2 is less than 0. My only critical value is x equals 2. These both lead to x equals 2. We say this is x equals 2 with a multiplicity of 2. Multiplicity means how many times does it repeat? So if I do my number line, my only circle is at 2. And I can test both regions. So I'll use 0 and maybe 10. I got 2 regions. 0 times -2, or 0 minus 2, 0 minus 2. This is a positive. It's less than 0. Nothing. You know what? I'm going to make this less than or equal to, so that we fill it in. If I plug in 10, 10 minus 2, 10 minus 2, 8 times 8 is 64. 64 less than 0, that's also false. So I had a false and a false. Only x equals 2 worked. If I had x squared minus 4x plus 4 is less than 0, then not even 2 works. And the reason why, that is x minus 2 times x minus 2 less than 0. X minus 2 squared less than 0. This is always a positive number or 0. Since I'm squaring it, it's always positive over 0, and that's never less than 0. So this one actually has, with just the strictly less than, no solutions. Note what happens if we do x squared minus, I'll use the same values because we've already got it solved. What if I say greater than or equal to 0? We'll do that on the next page. X squared minus 4x plus 4 is greater than or equal to 0. That was x minus 2 squared is greater than or equal to 0. That's going to be always true, but we can test it. Put a circle on the 2 and I fill it in. And I test each region. I'll use 0 and 4. I could use any numbers, but 0 is easy to use, 4 is easy to use. 0 minus 2 squared, negative 2 squared equals 4. 4 is greater than or equal to 0, true. 4 minus 2 squared is 2 squared is 4. 4 is greater than 0, true. It even includes the 2. X is all real numbers. X can be any real number. And the really fun one, do the same thing. We'll use greater than 0, but without the inequality. So we just tested the regions up above. We put a circle on the 2. We don't include the 2. But we know it's true to the left and it's true to the right. I don't know why someone in Arizona is calling me. It's true to the left, it's true to the right, but it's not true at 2. I could do an arrow going both ways. That's a little confusing looking though, because the 2 is not included. So I have negative infinity all the way up to 2. And then my interval starts again at 2 and goes to infinity. And it's 2 different regions. And that's what we do. In words, x can be any value except 2. Okay. Notice those regions did not alternate. Another scenario where you get non-alternating regions, I'll give it to you in factored form because this is not a pretty thing to factor. We will learn how to factor it later. x minus 1 times x minus 1 times x plus 2 is greater than 0. So I get x equals 1 with the multiplicity of 2. And I get x equals negative 2. Those are my critical values. If we multiply this all out, this is gonna look like there's gonna be a cube there. Ax cubed plus bx squared plus cx plus d greater than 0. Later, we will learn how to go backwards. How to factor a cubic equation. But I'm starting you with you in factored form. My critical values are at negative 2 and 1. I'll put a circle on them. I don't include either, so that are hollow. And I'll test each region. 0 makes a good test case. Maybe negative 10 and positive 10. And in each case, I'm plugging in the value into that factored value. Negative 10 minus 1 is negative 11. Then another negative 11. Negative 10 plus 2 is negative 8. I've got a negative times a negative times a negative. Overall, that's a negative. And that is not greater than 0. Negative values are not greater than 0. False. If I plug in 0, 0 minus 1 is negative 1. 0 minus 1 is negative 1. 0 plus 2 is 2. Negative 1 times negative 1 times 2 is 2. 2 is greater than 0. That's true. Looks like it's alternating, right? Let's check 10. 10 plus 2 is 12, or 10 minus 1 is 9. 10 minus 1 is 9. 10 plus 2 is 12. I've got a positive times a positive times a positive. That's going to be a positive number. It's going to be a big number. 9 times 9 is 81. 81 times 12 is pretty big. It's definitely bigger than 0. This is also true. So it looks like we're going to go from negative 2 to negative 1, not including either value. And from negative 1 onward to infinity. In interval notation, negative 2 to 1 in union with 1 to infinity. All right, finally, probably the hardest thing in this section, might be the hardest thing in this whole chapter, chapter 1, rational inequalities. And when I say hard, I just mean it's easy to make mistakes. Rational inequalities. It is easy to make mistakes. So be patient and go slow. So I'll just set up an example. 6 over x minus 3 is greater than or equal to 4. That's our example that we'll work with first. It's important to note you never clear fractions. we will find a common denominator and go from there. So what I'm going to do is I'm going to move everything to one side of the equation. Or the inequality, I should say. And make a giant fraction by finding a common denominator. Then, B, factor both top and bottom. Or numerator and denominator. Both yield critical values. The top, or numerator, use the inequality as is. And the bottom, or denominator, cannot equal 0. So this is going to generate a critical value or critical point that is not in the solution. So like a hollow point. Then we're going to do what we did before, find test points and proceed. Proceed as usual. Okay. The important thing to note is the bottom cannot equal 0, so those always make hollow points. They are not in the solution. Never, ever, ever. And that's why we don't clear fractions. If we clear the fractions, it's easy to lose that critical value, and it is a critical value. It does change the way the signs alternate, or whether or not they're positive, negative kind of thing. So let's go to our example of 6 over x minus 3 is greater than or equal to 4. I subtract 4 from both sides, and I get 6 over x minus 3 minus 4. I'm going to leave some room to write, is greater than or equal to 0. The common denominator is the only denominator here, x minus 3. So I'm going to multiply negative 4 by x minus 3 over x minus 3. This becomes one big fraction with x minus 3 on bottom, 6 minus 4 times x minus 3 on top, greater than or equal to 0. If I distribute, let's see, 6 minus 4 times x minus 3. I'm just going to do the work over here. That's 6 minus 4x plus 12, or negative 4x plus 18. So I've got negative 4x plus 18 on top, x minus 3 on bottom is greater than or equal to 0. I will solve each of these for 0. Negative 4x equals negative 18. X is 18 over 4, or 9 over 2, which is 4.5. Or we add 3 to both sides, x equals 3. Okay. Got 0 over here, 3 here, 4.5 there, or 9/2. I've got a greater than or equal to sign, so the top value, the one on top, I'm going to give a solid point. So I'll put a circle on both of them. 4.5 gets the solid point. 3 is a critical value from the denominator. It's from the bottom. It gets a hollow point. So I'm going to leave it empty. Then test each region. Maybe test 0 and 4 and 10. If I plug in 0, I've got 18 over negative 3 is negative 6. That is less than 0, so that's a false. If I plug in 4, I've got negative 4 times 4 is negative 16 plus 18 over 4 minus 3. This is a positive over a negative, which is negative. Hold on, positive over a positive, which is positive. 4 minus 3 is positive. So this is true. And then we check 10. Negative 4 times 10 is negative 40 plus 18 over 10 minus 3. Negative 40 is bigger than 18, so the bottom's negative. 10 minus 3 is 7, so the bottom's positive. So a negative over a positive is a negative number. Negatives are less than 0. This is a false region. So apparently the only region that works is in the middle. It's between 3 and 4.5. We don't include the 3 because it was in the denominator as a critical value. 4.5, I'm going to go back to 9/2. And we include it. So bracket. Let me give you guys one to try it, and then we'll solve it together. And then we'll be done with this section. (3x plus 1), that is all over 2x minus 3. And we're going to say this is less than or equal to 4. And you try. Pause the video and try to work this out. Take a drink of coffee, gives you a pause break. All right. I know I'm going to need a common denominator, so I can do the 2x minus 3 now. If I subtract it over, I got minus 4 times 2x minus 3 over 2x minus 3, less than or equal to 0. (2x minus 3 is on bottom. I've got 3x plus 1. I'm going to distribute. Negative 4 times 2x is negative 8x, and negative 4 times negative 3 is plus 12. Combining like terms on top, I've got negative 5x plus 13 over 2x minus 3 is less than 0. So critical values. This is less than or equal to. I don't know why I dropped the equal portion. The top, negative 5x plus 13 equals 0. Gets me x equals 13 over 5. And in decimal form, that's 2.6. Bottom, 2x minus 3 equals 0. So x equals 3/2. X equals 1.5. Zero is to the left, 2 is in the middle, 4 is to the right. I'm going to put a circle on the 1.5, a circle on the 2.6. I'm going to fill them in now. The top had an equal portion to it. The top was 2.6. I'm going to make that solid. The bottom was 1.5. It cannot equal 1.5. So that's going to stay hollow. And now let's test the regions. If I plug in 0, I've got 13 over negative 3 is negative. That's a true statement. Negative value is less than or equal to 0. If I plug in 2, I've got negative 10 plus 13 on top. 4 minus 3 on bottom. 13 minus 10 is 3. 4 minus 3 is 1. That's a positive number. Positive numbers are not less than or equal to 0. That's false. If I plug in 4, negative 5 times 4 is negative 20. Plus 13 over 2 times 4 is 8. 8 minus 3. This is negative 7 over positive 5. That's a negative number, which is less than or equal to 0. That's true. So we're going to go to the left, and we're going to go to the right. Left of 1.5 and to the right of 2.6. And just to keep it on the same page, I'll do interval notation above it. Negative infinity to 1.5, parentheses, in union with bracket 2.6 to infinity. That wraps up 1.7. We covered inequalities. We covered quadratic inequalities, linear inequalities, quadratic inequalities, rational inequalities. In 1.8, we're going to do absolute value inequalities. Good times, good times. Yes. Remember, when you divide or multiply by a negative, you need to flip the inequality. Always, always, always. All right. That's it for this section. Peace.